All right, cool. Hopefully that'll focus. So what we did, we developed two formulas starting from the same base place. Believe it or not. We had, that's too dark over here. This old formula, and we started with that and we created two things. And I kind of approached it from several different angles, but basically we normally don't know this. We normally only know X bar. If I get an X bar, I must have taken a sample. Therefore, the standard deviation has to change, since I'm talking about sample means. So that becomes this. And this, the idea is, if I want to create a 90% confidence interval, if I make an interval that catches 90% of the information, how confident am I that I caught a specific piece of information? 90%. So I always think that, now this could be just me, but I always think that it's almost like it's too easy to believe that it's that easy of an idea. That if I just go far enough out, then that's how you construct the interval. That's exactly how it works. So if I wanted to make a 90% interval versus a 99% interval, the 99% interval is going to be bigger because I want to catch more shit to be that confident. Yes?
So like let's say 96 compared to 90, 96 grams more of a population. Like, okay, if I had 90 compared to 96 as an interval percentage, so the 96 would be more of a population. It's still a sample, but like, it defines more of a population.
So what you're really doing is you're catching a percentage of the population of all sample means, to be honest, when we do this. So I just kind of simplify to say you catch that percentage of the data, right? And the data in this case is going to be, in this case, sample means. I like it. So yeah, if you want to make it 96% confident, you just got to catch more of it to be a little more confident you caught a specific one.
So, I think it's the n equals.
Oh yeah, we're getting there.
So for that equation, how come you don't use like standard deviation of like a sample? Why do you use a
So here's the beautiful thing. In fact, in the book, they will sometimes give you both. In fact, so in section 8.1, come with me on this journey, really, Jeff? You're going to say, come with me on this journey, kids. So we do sometimes know the population standard deviation. So for example, we talk every now and again about testing water to see if it has too much of some cancer-causing agent or something, right? Testing some water samples. So there's a standard deviation of amounts of some mineral or some chemical in water supply. There just is. You guys with me? And there's got to be below a certain threshold, and it's okay then. So we're always ingesting, who knows what we're ingesting, just small enough so it doesn't really do anything to you. So we have we might know the standard deviation for all water, how much of a certain chemical is in all water. And then we go to a specific town. You with me? I mean, this is a real situation. We go to a specific town where there's been more incidences of cancer, certain kind of cancer, right? So we go to the town, we take a sample of water. If I take a sample, can't I calculate the sample mean amount of that chemical, right? And can't I calculate the sample standard deviation? So I really want you to, so we have this big ass population of all water. And then there's some amount of chemical. So I know the average amount of chemical and I know the standard deviation of the chemical. The amounts of chemical in there. You guys with me? Across different water systems. Well, however you say that. I'm not a water guy. I just drink it sometimes. You guys semi with me here? So there's a water delivery system in the United States. We happen to know the average and standard deviation of a certain kind of chemical in the water. Right? You guys semi with me? Are you guys with me on that? Okay. Then there's a little town down here. Right? Little tiny town. It's got one stoplight. But they have a higher incidence of a certain kind of cancer. So we go in, we want to investigate. We think, well, it seems like maybe it's related to this chemical. So we go in and we take a sample of water. And we get a sample mean and a sample standard deviation. And what we want to do is we want to construct a confidence interval for their water. Because we're taking a sample of water from the town, right? We're not taking all the water in the town. You guys kind of with me. I know this for all water, and I know this for the sample of water I took. Which one is the better one to use? They're both true. Which one's the better one to use? Population one is the better one to use because it's the true one for all water. If I happen to know the population standard deviation, it's going to beat the shit out of any sample I take.
But isn't the sample one more specific to?
But what we want to see is this town weird compared to the entire population? It is still a part of this population for which this is true. So, in a problem, if you are given sigma and S, screw S. S is an estimate you only have to use if you don't know sigma. Is S correct? No. It's sort of like, of course I would use this instead of this if I knew this, but we're trying to estimate what this is for the town. If I knew it, I would use it. I would be done. So I always use population information if I have it.
If you don't have it, like, would you just?
That's section 8.2. And the reason I skip section 8.2, this should make some sense. If I don't know this guy, if I'm uncertain about this guy, and he determines the shape of the distribution, how fat or skinny it is, I'm going to have to cover my ass for that somehow. So that's why it gets its own little section. That's why I skip it, because it uses, you're going to love this shit. I got another chart, another distribution. Oh, yeah. So when I don't know standard deviation, I've got to somehow cover my ass for that. And I'm going to use a phrase later to explain what happens with the scores we use. We're not going to use z-scores. We're going to use something else. Oh, I'm so excited. Probably more than you. All right. Does everybody get that? That's a good question. I love it. That's exactly the kind of question I want you guys to be thinking about. And that's exactly why section 8.1 is not quite true to life as much, but it still are situations where I do know this, and I take a sample from that population. Of course I'm going to use that if I know it. Now there's a lot more situations where we go in somewhere and we don't have a clue about shit. So all I got then is S. If I go into another, for some reason I'm thinking about arachnophobia now. You ever seen the movie? You go into this little area and you take spiders and you take their average length of the spider, right? Sorry if you don't like spiders, but too bad. Do I know anything about that region I'm in? I don't know shit. Do I know the standard deviation of spider lengths? No. So what's the next best thing I can use? S. I don't have sigma. I have to use S. When's the only time you have to use S? When you don't know sigma. That's the ultimate thing to know. S is just an estimate for this guy. You guys with me a little bit? So section 8.2, we are skipping it exactly because I have to give you a different chart for a different distribution. 8.1 and 8.3 both use z-scores. That's why I think the book just has it out of order, so I fixed it. Yeah. FTF1.
Question about that formula. I just want to understand it better. So for, you know how you have like plus or minus for that one? Because there's two parts. And then for the other one, it doesn't have plus or minus anywhere.
What other one?
The n equals.
Of course it doesn't have plus or minus because n has to be positive.
So when you square, is that what substitutes for?
No. So, real quick, What do we call this part of the equation? You guys remember? Error. E. So E equals what? Not MC squared. E equals this, right? E equals this. There's no plus or minus there. So it's our best guess for the average, give or take how much I think I'm off by. So the error is this. So however I think I'm off by, however much I think I'm off by, aren't I going to add and subtract that? That's what off by means. I think it's 90 miles away, give or take 10, give or take, plus or minus, how much I think I'm off.
But isn't it only going to give you the distance from, like, the positive? So, like, you have...
No, you're overthinking this. If I said I want you to be within 10 miles of how far away Washington, D.C. is, right?
Oh, because
10 miles either way. So don't think about, if I make an interval and it's 4 to 7, yeah, it's 3 wide, but what's the error? 1.5. That's how far away either is from the middle. That's how far I'm off by, right? I did say 1.5. Thinking back to my memory. So it's 3 wide. Isn't it 1.5 away from the middle? What's the middle of 4 to 7? What's the middle?
7.
No, 7 can't be in the middle of 4 and 7. 5.5. What's one way to do that real quick? Aren't they 3 apart? Half of that is 1.5. Add 1.5 to this, you get to the middle, of course, because that's halfway. And that is the error. That's not the error. 1.5, that number I got a minute ago, that's the error. That's how much I go up and down from 5.5. That's how much I think I'm off by. So this would have been the mean I got. And this would have been the amount I added, subtracted. That's the amount I think I'm off by. Okay. All right. So we worked with, actually, did we? Yeah, we did this, didn't we? We solved this for n. Remember this correctly? We got that multiply, we divide, and then we got this little dude. Jaboo. So when you use this equation, when I ask you how many do you need to be within a certain amount, kind of makes sense. I'm asking how many you want the equation solved for n. Okay. Right. Any questions about anything that's happened so far? You guys doing all right? Relatively? You're like, as okay as it can be in a freaking stats class. All right, I'll accept that. So that's one equation we made. And then we did some examples with it. And I freely admit that it's very rare that we actually know this, but there are situations where we do. So in section A2, we're going to put an S there. And then this can't work here. We'll get there. We then started from that place again. And we developed a formula for percentages so that we can finally see where the news, do you guys know about the news? Some of it's real. And when they give a report about, 55% want to vote for this and whatever, and at the bottom, plus or minus 4%, well, now we see exactly where that plus or minus percentage comes from. This, if it comes out to 4, then it's plus or minus 4%. So now we finally see the math behind that number. Which I don't know if anybody appreciates that. I don't know. I mean, that should kind of be, you've seen that number before this class, the plus or minus 3, plus or minus 4. I'm sure somewhere you saw that and you're like, what the shit did that come from? They just make that up? I don't know. Plus or minus 7. Sure. No, it comes from the actual math. And if my sample gets bigger, what happens to the error? Gets smaller. It makes sense. We knew that day one. Bigger sample, better. Good, big sample, good. Yeah, right? So we knew that. So n bigger makes the error smaller. That makes sense. So the math agrees with what we know, which is always nice. Okay. So what we haven't done yet is an example using this. So let's try this bad boy out. What do these little hats mean anyway?
Sample.
Sample stuff, right? Sample percentages. Let's say that I talk to 80 parents and find 68 have decorated for Halloween. Find the 90% confidence interval for the true percentage of parents who have decorated. So we're going to take a little side trip here. Because what is it for means? When I have a problem about means, what do I have to be careful about in general? So for example, just to get you back, what part of this equation does this help me figure out? I want to be 90% confident. So what's that going to directly lead to? Z-score. And where are you going to get that from? Chart. Crazy. But what's the only time I'm allowed to use that chart? When I have a normal distribution. Do you know that's normal anywhere? Does it say anywhere that it's normal? Oh shit. If it was means, what would we check? What makes a mean? If I don't say it's normal, what do I check to see if means have a normal distribution of sample means? Sample greater than 30. Kick ass. Is this problem about means? Is this problem about means? It's about percentages, right? Shit. Damn. I had a test ready if it was means that I know and we've used it. We all know n greater than 30 is good. And this ain't about means. Damn it. So, what we do? I again forgot to bring this thing, but remember that handout I gave out a while back that had the big histogram in the middle, flipping a coin 14 times? And it had this. Right? And if I would have drawn it better, you could see that it does look normal, doesn't it? And this situation was flip a coin 14 times. How many heads do I get? So, of course, P was 0.5, right? What's the mean for that then? Well, don't even think about that mathematically. Just think about it. If you flipped a coin 14 times, how many heads do you expect to show up? If you flip a coin 14 times, how many heads do you expect to show up on average? 7. So the average is 7. Mathematically, it's n times p, 14 times 0.5, but we frickin' can just think about it and know what makes sense. Okay, I like it. So it's always nice to see math matches with what we would just do in a simple situation. Somebody with me. And of course, wasn't the mean the biggest bar? Right? The mean was 7. So doesn't it make sense that whatever the average is, the tallest bar, it turns out it isn't always exactly equal to that, but it should be close. Stay with me. Come on, stay with me. This is so cool. And I know it's probably just me, but that's all right. So why is this normal enough? Because the mean was far enough away. What's the least this could have been? The number of heads I get when I flip a coin 14 times? 0. So there's a wall there, isn't there? There's a wall there. So what's the lowest the mean could be for a situation where at 14 times, the lowest is 0? And the highest, of course, is 14. You guys with me? So the mean, in this case, of course it was, right in the middle. Because P and Q are 0.5. Isn't that going to make it symmetric? They're 50-50. It's going to be right in the middle. So there's room for it to grow and then shrink, just like a human. We grow and then we start to shrink when we get older. You don't have to know that last part. Yes? No, hell no. Why was it 0.5 here? Because I'm flipping a coin. Say again? In this problem, it was flipping a coin, a fair coin, so it's 50-50. If I'm talking to people and 20% of them like liver, then P would be 0.2, right? So P is whatever it is in that situation. Here it was because I was flipping a coin. That's why it's 50-50. It isn't always 50-50, unfortunately, which is actually my next point. I love it. So, I really want this to make sense. Why was this normal? Because the mean was in the middle somewhere, so it had room to go up and come back down. What the shit do I mean? What if the mean would have been, what if instead of this, what if I had this? Let me come over here. What if n was 14, but p was 0.01? What's the mean then? So I got a really heavily weighted coin. N is 14, but P is only 0.1. There's only a 1 out of 100 chance that it's going to come out to be a head. 0.14, right? You multiply N times P. So the mean would just be 0.14. And again, what was this wall? 0. And what was this wall? 14. 0.14 is going to be where the highest bar is close to. So it's basically going to start high and go low. Does that look normal? Why not? Because the mean wasn't far enough away from that wall, so it has room to go up and then come back down. So what we discovered is that as long as the mean, NP, as long as that mean is at least 5, if it's at least 5, if it comes out here to 5, then it's got room to grow and room to shrink. Really, yes.
Is this for any sample size?
Yes. Yep. Because again, means n greater than 30. We're trying to develop a test now for percentages. So this is half of that test, yes?
So would that mean that it would be otherwise?
All right. But there's another freaking wall, right? So the mean can't be too big either. Yes.
So what if there's like a sample, like you're told that it was normal, but it's only like 6, a size of 6?
Well, if you're told it's normal, you're fine. That's all.
Oh, we're just trying to figure out if it's normal?
We're trying to figure out what if they don't tell me. So for means, if they don't tell me it's normal, what do we have? N greater than 30. We have something we can check. Correct?
We need to know how to
If it's not normal, we can't do shit. Because what do we immediately want to do? What got me going on this whole thing? You're all like, we don't know. Whatever it was, we don't want to let it happen again. Because I don't know what the flip you're saying, dude. Can you guys get that this had room to go up and come back down because the highest bar was in the middle somewhere. In fact, it was 7, which is bigger than or equal to 5, isn't it? Yes. This one, the highest bar is going to be right next to 0. Does it have room to go up and come down again then? Shit! So this keeps it from being too close to this wall. Now I'm just going to put this other one. Isn't there a whole other wall, right? So the nice thing is I can do this, n times q. If that's also at least 5, then it keeps it away from both walls. Yes?
I'm just wondering, like, if, say they had, like, a sample that was, like, only 6
Sure.
amount of, like, people that they served or whatever, then wouldn't it be, like, you have 0 to 6, right? And then it would be all the way to the right. That's why.
Well, I don't know what P. He didn't tell me what P is, so how would I know what the mean was?
Sure.
All right, but if you only had 6, there's no way that both of these can be bigger than 5. Do you see that?
Because NP, isn't that equal to the mean?
NP is equal to the mean, yes. And on this picture, where was the mean? The tallest bar. So, again, I love you guys so much. You should be getting some of this idea, at least. I think you're all worried that you're going to have to somehow be able to do what I'm talking about again yourself. That's shit. What are we doing? N greater than 30. How long did it take me to explain that? For frickin' ever, right? And I'm hoping some of you guys picked up what I was laying down, but maybe not. But we ended up with N greater than 30 is a check. Why? Because Jeff said some shit, and that's why, right? But at least you got some record of what I said, so maybe you can go back and see why it makes sense. What we're doing right now is we're developing, in fact, we have developed a test for percentages. That's what I check. Whatever the situation is, I check to make sure that these two things are true. This is in place of N greater than 30. That only works for means. This is for percentages.
So if those two are true,
Then it's normal enough.
Both have to be true?
Both of them. And again, it's because one level of this, I'm hoping that you guys, one level of this is simply, where can I put the highest bar and it still can look normal? In the middle somewhere, right? That's the only way. If I put the highest bar here, does it have any chance to look normal? No. That's what this takes care of. If I put the highest bar over here, again, there's no chance. It's only going to go down from there. How could it possibly look normal? So these two together force it to be the highest bar in the middle somewhere. So it's got room to go up and come back down. Personally love that idea. It's an awesome idea. But again, I think some of you guys are worried about what you were going to be responsible for. In this problem I gave us, we can check it real quick so you can see a concrete example. Does somebody have a... Yes?
So like, what would another section be like?
Got what now? Sorry?
What would this connect to real life besides the question asked?
All right, so one of my personal favorite questions is anything we do in here that's got highly statistical analysis meanings, and then you say, what does that have to do with real life? And what you really mean is, every day, where am I going to see this? No, it's not going to happen, right? We are learning how to do things that you might never do every day unless you go on to become a statistician. Or you go on to become... I love it. You don't have to react that violently against that suggestion. I'm sorry. So you're like, hell no. I know it for sure now. All right, sorry. But what I'm trying to do here is, for example, we are getting to a point where if I ask people an opinion and I get an interval from 38.7% to 48.2%, right? That's an interval, a confidence interval. I am 90 whatever percent confident that the real percentage is between those, that interval catches the real percentage. Are you guys with me a little bit? That's the same language you use. Thankfully, it's the same language you're going to use for the percentages. Is that evidence that the percentage is less than half? What do you mean? What do I mean? Is this an example that it's less than half of people?
Yeah.
This is evidence, right? So I could say we've clinically tested it and it came out to be evidence that less than half of the people want this. Or, you with me? If another one was this, is that evidence that it's less than half? Because it could be more than half. So one immediate thing I can do with any confidence interval I create is to see if it's strong enough evidence for or against some statements, right? So when they say, we tested this clinically and 3 out of 4 dentists agree, well, that's 75%. They found evidence that it doesn't exclude that it could be 75%. Are you guys kind of understanding? So that's the immediate thing I could do when I start creating confidence intervals. Yes? I answered it. Sweet. I love it when that happens. Okay. All this is beautiful, right? I love that you want to know why. Will you necessarily have to use this when you go to the grocery store? Well, no. But if you're level of checking to see if something is worth it is, do I need it to go to the grocery store, then your life is going to suck a little bit more than it could have, right? So we want to learn things so that if I want to interpret a study that somebody put out, and I hope you guys are inundated with stuff all the damn time. You log into Facebook once, and I don't know, Facebook, Instagram maybe, whatever the shit you guys are using. TikTok, I don't know what the hell you guys are. I don't even know what that is, to be honest. I'm kind of happy about that. So I don't even know what I just said. I don't know what TikTok is. You have to be able to interpret some of the basics to even see if you can trust what they're saying. I mean, how much false shit is out there now? So much. Why? Because they know nobody's going to check and they're just going to take it on the surface. We have got to know what to look for and have a little feel as to what goes into it so I know if it sounds right. Don't just say, oh, really? Holy shit. Well, screw them. No. Who is it? What could their motive be? Who did they talk to? Did they describe any of their sampling methods? Anything. So that's the very least I want you to come out of this class with is, if somebody tries to convince you of something with an article, with percentages, with this big layout, I want you to at least know what to look for. Yes?
You know those questions that you ask on the test, like, how do you know this is what you're supposed to do? Would it be like sufficient if you just wrote these down, like NP is less than or equal to 5?
Randy, yeah, so if I say check NP and NQ for normality, right? That's got to be true. In fact, it's part of the steps of what we do. N greater than 30. We have to say that to show that that's why we can do something. That's why I'm allowed to use the z-score chart. If n's greater than 30, if they don't tell me it's normal, right? So this is a check, just like n greater than 30. Is it as small and nice? No. Is it extensive? No. Shit. How do I know to use this one? Because percentages are in them. So when you have a percentage problem, you use the check that involves percentages. Excuse me. Okay. So all of that we just discussed, we got here. So for example, on this problem, you guys help me out. What's the percentage I see from the sample that I took? What? Say again, sorry. I must be going deaf or something. It's entirely possible.
90%.
No. That is how confident I want to be in my interval. What percentage do I get from the sample I took? And I'm glad you guys said that. That is a part of this problem that sucks.